Next, I want to talk about something called entropy and free energy. So, in chemistry, there's this law called the law of disorder, and it states that the natural tendency is for systems to move to the direction of maximum disorder, not vice versa. So, it's not natural for things to become ordered out of nowhere. Generally, just through the course of chemical reactions, we make more randomness and more disorder in the universe. If you have an increase in entropy, that favors a spontaneous chemical reaction. If you have a decrease in entropy, that favors the non-spontaneous chemical reaction. So we should probably define what entropy is. So entropy is just a fancy word for disorder. So it's a measurement of disorder. So you can quantify entropy. We don't need to do that in Regents chemistry. We just need to know what it is. So it's just kind of word association. Entropy means disorder. You also need to be able to judge what scenarios or what conditions have more or less entropy than another. So I have three states of matter here: solid, liquid, gas. So which of these has the most order? Which of these has the most disorder? So if they ask who has the highest entropy, of course that's the gas. Liquids have more entropy or disorder than solids, but less than gases. So as we can see here, the solids have this regular repeating shape. They're all bonded nicely to each other, and they are keeping this rigid structure here. So that's a lot of order. Liquids do not. So the intermolecular forces are weaker. They're flowing and slip sliding past one another. They're taking the shape of this container. They're moving more than they are as these solids. So this has more entropy than a solid. But gases have the most entropy. The intermolecular forces are very weak, so they are moving away from each other. They're no longer connected. They have higher kinetic energy. They're bouncing around. That is more randomness and more disorder or entropy. So we could also look at just structure as well. So in this picture here, this is showing increasing entropy from left to right. So as this solid block, this has more order to it, but if you hit it with this hammer and break it into all these random pieces that are falling off the table here, that's more randomness, that's more disorder or entropy. We could also judge entropy in a chemical reaction. So this is a reaction showing the electrolysis of water. So we have 2 moles of liquid water, and we are decomposing it with electricity to make hydrogen gas and oxygen gas. So this is showing increasing entropy from left to right here. So these molecules of water have more order to them. There's bonds going on here between the different atoms. So a lot of order and structure. But as we break it down with electricity, not only are we turning one molecule into two, or if we look at the balance values here, 2 molecules into 3, that's more disorder. That's more random. Plus, we're turning a liquid into a gas. And like we already said, gases have more entropy or randomness than liquids do. Next, we have 3 liquids here in various states of being heated. And of course, the hottest one, the furthest to the right here, has the most entropy. So these particles are moving faster than either of the first 2 pictures here. So they are more random in their movement. They're moving faster. They have more kinetic energy. So most entropy in this picture, least entropy in this picture. This picture is an intermediate amount of entropy. So let's look at some example entropy questions from past regencies. So given the equation, we have solid potassium nitrate, and we are dissolving it in liquid water to make aqueous potassium nitrate. As the H2O liquid is added to the solid potassium nitrate to form aqueous potassium nitrate, the entropy of the system does what? Increases, decreases, or remains the same? Well, like we said earlier, entropy of liquids, which is what an aqueous solution is, it's a solid mixed in a liquid, but it will have all the same properties of a liquid, has more randomness to the particle arrangement than solid potassium nitrate. So entropy is going to increase. Which 10 milliliter sample of water has the greatest degree of disorder? So let's look at our choices. We have gas, 2 liquids, and a solid, and we also have some temperature values. So the one that has the most randomness or the most disorder, there's two different ways you could answer this question here. So we talked about gases being very random, but also look at the temperature. The hottest one, the highest degrees Celsius here, is also going to give it a lot of randomness or a lot of entropy, a lot of disorder. So choice 1 is the best answer here. How about this one? Given the balanced equation, which statement best describes this process? And if we look at our choices, we have a choice between endo and exothermic, and entropy is increasing or decreasing. So first we need to decide whether it's endo or exothermic. So if we look at the energy values, the 34.89 kilojoules, that is on the left. That means it's a reactant. So energy is being absorbed into the potassium nitrate to break it down into potassium ions and nitrate ions. So that, of course, is an endothermic process. And then, so we've eliminated choices 3 and 4. So as solid potassium nitrate breaks down into two separate ions, potassium ions in an aqueous solution and nitrate ions in an aqueous solution, is this more ordered than the original potassium nitrate or more disordered? Of course, it's more disordered. So entropy is going to increase. If you make two things from one, that is an increase in randomness or increase in disorder. So reactions always tend to proceed in the direction that decreases the energy of the system or the enthalpy of the system. So if energy content of the system is going down through, like, say, an exothermic reaction, we're releasing energy out into the surroundings, that is a decrease in energy or a decrease in enthalpy. But reactions also tend to proceed in the direction that increases the disorder of the system or increases the entropy of the system. So these two things are drivers to every equation. So this is kind of what's deciding whether the equation is going to happen spontaneously or not. So if they both agree, meaning that the reaction is going to decrease the energy content but increase the entropy, then the reaction will be spontaneous, and it will be spontaneous at all temperatures. If they both agree that the reaction should not be spontaneous, it will not work at any temperature. If one agrees and one doesn't, then something else comes into play called Gibbs free energy. But we're not going to talk about that in Regents chemistry. If you take AP biology, we'll get into a discussion of Gibbs free energy. So in summary here, entropy means disorder. You just need to have that word association. If you see the word entropy, you can just replace it with the word disorder. And you should be able to judge which conditions have the most or least entropy. And you also need to know that the natural trend in the universe is for lower enthalpy, meaning less energy, and higher entropy, more disorder.